Hello, we are teammates, and this is our paper presentation about MOCHA real-time motion characterization via context matching. Our presentation will start with an introduction about MOCHA and its framework, and will move on to its training and evaluation. So what is MOCHA? MOCHA is a framework that transforms neutral input motions into distinctive character motions in real time by transferring both motion styles and body proportions from a target character. For example, if Princess was a character, simple motion of walking or sitting will be transformed into a more elegant movement as shown in the video. How does it work? This is the overall framework of MOCHA. It takes a source motion as input, goes through body part encoder, neural context matcher, and characterizer, and returns a characterized motion. Let's follow them step by step. First, they take in the input source motion. MOCHA represents motion using a set of vectors. This is a picture of a right elbow of a figure in a certain frame. Here, the vectors xt, xr, and so on will each represent joint translations, joint rotations, joint linear velocities, and joint angular velocities, adding up to 15 in total. There will be more than just one joint in a figure, and all those joints should be considered to represent a motion. These information combined will make up a representation of a frame of a motion. Then we will have to repeat this process for each frame to make up a representation of an entire motion. The representation method will be the same for the output motion. This input will go through its first step, body part encoder. Body part encoder consists of two parts, body patch embedding and transformer encoder. Body patch embedding reduces the spatial and temporal resolutions of the input motion while preserving body part structure using spatial temporal graph convolutional blocks, so STGCN. How does STGCN reduce the resolution? To understand this, we have to know the receptive field of STGCN. STGCN represents a figure like this, with nodes and edges. Each node contains information about itself and the information of the adjacent nodes. For example, the node of a left elbow will also contain information of left shoulder and left wrist. This state would be GCN, but STGCN takes temporally adjacent nodes into account. So this left elbow will contain information of not only left shoulder and left wrist, but also information of the left arm of previous frame and the next frame. Just like this. Then, we flatten the motion data while preserving the positional information by adding positional encoding with learnable parameters. This calculated sequential feature embedding is then sent to transformer encoder, which is used to capture spatial temporal dependencies among the body patches, learning how different parts of the body move in relation to each other over time. The transformer encoder consists of multiple layers, each with a multi-head self-attention module and a feed-forward network. MMA first takes in the sequential feature embedding and applies weight, or you can say importance, to different body parts. The result is passed to FFN, which further processes the results into a higher level representation. After body part encoding, MOCHA searches for a character feature that shares a similar context with the source feature using neural context matcher. From the source feature, MOCHA obtains context feature via context mapping. This context feature is character agnostic, which is necessary for context matching between different characters. The result of current source context mapping and the previous character feature is sent to prior nets to parameterize a Gaussian distribution, resulting in possible latent variables. This step helps maintain temporal coherence, meaning that the transitions between frames are smooth and the character's motion appears natural and consistent. The result is then passed on to NCM decoder along with the conditions per net. NCM decoder uses transformer-based autoregressive conditional variational autoencoder model to predict and generate the next character feature. The last step of MOCHA is Characterizer. The source feature and character feature generated in NCM is passed on to character transformer decoder in Characterizer. The inner structure of it looks like this. Adain is the same one mentioned in our lecture presentation, so we'll move on to the next step. But just in case you forgot, I'll provide you a brief explanation. Adain considers the statistics as style, and so it injects the global statistics of character feature calculated by NCM by injecting the mean and variance of it. The next step is multi-head cross-attention and FNN. Context feature generated by Adain, character context feature and character feature multiplied by weight respectively is used to generate query key and value. The result is added with the results of Adain, then passed to FNN to integrate detailed style information from the target character into the source motion, maintaining the source motion's context. The translated feature is upsampled with the STGCN blocks, which is just symmetric operation of STGCN mentioned at the body part encoder part of the presentation. However, in the process, MOCHA maintains the root angular velocity of the source motion while scaling the linear velocity according to the ratio of the average hip velocities of the source motion and the output motion in order to maintain the overall shape of the root trajectory of the source motion.
Next, I will briefly introduce the training part of this model. There are two stages of training in this paper. First stage is training body part encoder and characterizer. This training is conducted on an unsupervised way, and body part encoder extracts encoded features from a motion. Then characterizer transfers style aspects of one motion to the other motions, such as motion style and skeleton proportions, to synthesize characterized motion. Second stage is training NCM, which is neural context matcher, in a supervised way to generate target character features corresponding to the input context features from the source. Let me explain more deeper of this stage 1 training. Without NCM, we randomly choose source motion, which is X subscript source, and character motion, which is X subscript character, to train the body part encoder and the characterizer jointly. When we do learning style transfer, we usually use identity and cyclic consistency loss. Also, the authors introduced a contrastive loss to enhance local context preservation spatially and temporally. I will tell you what meanings these losses have in the next slides. To design identity and cycle consistency losses, the authors first defined the reconstruction loss. This loss computes difference of two motions in terms of x and y. One of the motion is reconstructed motion, and x equals forward kinematics of y, since we can calculate final position by using each joint's rotation and translation. Vx is the rate of change of x, which corresponds to accelerations of joint, and the lambdas are all relative weights. By using this reconstruction loss, we can define identity loss, which ensures that input motion remains unchanged when it is used for both the source and character motions. X with a superscript ID and a subscript source represents characterizing and applying forward kinematics of Z subscript source. This Z subscript source means applying body part encoder of input source motion. Likewise, we calculate reconstruction loss for character motions in the same way. Also, we employ cycle consistency loss to guarantee that result motion Y subscript translation preserves the context of source motion and characteristics of character motion. X with a superscript cycle and a subscript source means applying the same body part encoder and characterizer by using Y subscript translation. This result motion is used again to calculate loss, so it is called cycle consistency loss. By calculating loss of character motion in the same way that I mentioned, we can preserve context and characteristics. Lastly, the authors defined body patch contrastive loss to preserve context of body patches at specific location across characters. For example, the context of a princess leg at frame I-T should be closer to that of input zombie leg at frame I-T than the other body patches of the same input. To define this contrastive loss, we use info NCE loss, which is as follows. This tau is just the temperature parameter, and each V plus and V minus is positive patch and negative patch. So for a characterized body patch FZ translation, we set this positive patch FZ source as the patch in the same location in Z source, and negative patches are FZ source with large B without B, since small b is specific body patch and large B is total number of body patches. So simply positive patch means body patch with similar location, and negative patch is the opposite ones. Anyway, the important part is that this contrastive loss considers locations of body patches. So finally, we can add these three laws to get final stage 1 loss. Next stage is training zero context matcher. Since NCM is an autoregressive conditional variational autoencoder, training NCM encoder and decoder is conducted with sequence of source features and corresponding sequence of target features. NCM transformers take previous character feature and current source context feature to reconstruct context-matched target character feature. It uses KL divergence loss, which deals with latent variable distribution, and latent variable loss, which minimize difference between decoder-generated target feature and real target feature. At runtime, encoder is discarded and only decoder is used. Finally, let me explain the evaluation and experiments of this model. First, these 6 characters are used for datasets. These are 5 emotions, and this dataset has 573K frames with 60 FPS. Also, the authors use adult to child dataset for quantitative evaluation. Each subject, such as 9 adults and 8 childs, are used as a character. The authors first introduced the result of qualitative evaluation. In the figure, source is a neutral average Joe character, and there are our model, nearest neighbor, which is MOCHA without NCM, and motion puzzle. Nearest neighbor and motion puzzle requires specific reference motion, so it is manually selected, and this is the target character performing most similar action. As you can see, MOCHA better preserves unique styles such as limping legs of the neutral zombie or energetic waves of the angry clown. Nearest neighbor exhibits discontinuity compared to our model. Then the authors conducted quantitative evaluation. Metrics were Frechet motion distance, context recognition accuracy, and style recognition accuracy, which are used in motion style transfer. As you can see in the table, MOCHA achieves superior FMD and SRA scores. By this result, compared to motion puzzle, our model achieves higher motion quality and precise style reflection, and compared to nearest neighbor, we can find the significance of NCM. Authors also conducted ablation studies to find out effectiveness of ADA-in layer and contrastive loss. First, the effect of ADA-in is that it facilitates successful characterization. For example, by making ablated model which does not have ADA-in layer, this model cannot capture the ogre's raising arm style. Next, authors conducted ablation study with removing contrastive loss. The effect of contrastive loss was preserving spatial and temporal context across characters, and this is shown by experimenting model without contrastive loss. The ogre's left and right legs are swapped, which is because attention module alone may mismatch. This MOCHA model can be applied in various situations. First, input from unseen subjects with different body proportions can be effective, as you can see in figure A. Second, sparse input such as reduced input joints to only 6 can work with our model. This is shown in figure B. Finally, this model can characterize stream motion data in real time, as you can see in figure C. Finally, there are several limitations in this model. It is effective when motion contains single character style per context, so different styles sharing same context may be a problem. Second, context mapping is effective without manual style labels, so it is not flexible enough to encompass all stylistic diversity. For example, it could not link exact running and jumping part to other characters. In conclusion, the thing is that MOCHA can transform user motions to embody distinct style of characters in real time. We prepared 2 questions for quiz. This is the quiz link and it will be easy enough if you followed our lecture well. And these are our references. This is the end of our lecture and I hope you better understand what MOCHA is. Thank you for listening.